Then we'll round off with the quantification of model performance. So we'll speak about how do you actually quantify performance of a model in machine learning. Because if we don't know this, then it's difficult to say this model is better than this and so on. Following that, we'll have these 7 exercises to show some of the most important features from these 3 categories. For example, you can detect bumps or cuts in seeds. So some of them might have some protrusion or some valley, you can say. Maybe they have some repetitive texture, or maybe there's a texture that has some direction. You can measure that too. In wheat, a wheat kernel has 2 sides, such as this one, where it can either be up or down. You see the side or the line cutting through. That's only present on one side, which we call the ventral side. So you can measure that as well. So shape features, they measure the overall shape of the blob, and they operate on the blob mask. So here you see on the left, you have 4 seeds and their corresponding masks. And you use this mask then to generate some kind of number. So, and here's a long list of the most used shape features. So, and we'll go through some of the most important ones. For example, you could measure the compactness, so how circular an object is. So the higher this number is or the closer to 1, the more circular it will be. So something like this, very circular, but not perfect. So maybe it's going to be quite close to 1. These are more elliptical. They'll be far away from 1. Some other measures, similar measures, eccentricity, form factor, roundness, they measure essentially the same thing. You can also measure, let's say, and I'll get back to this, you can measure how long they are. So, and also the ratios between those. So for example, this seed here is very long compared to its width. I mean, this one is even more. But this roughly circular object, the length is as large as its width. So the ratio would be around 1. And many more type of features where you can measure if there's a hole in the blob. You can measure the perimeter, how pointy it is. You can even get the volume or some estimate of the volume. But again, we'll get back to this. So this is just a rough overview of what we'll talk about. So one feature that is, you can say, quite simple, but maybe sometimes it's used for detecting skewness in blobs. So area fraction, you can return the ratio of the area inside this region of interest to the total area. So if you choose 100, then you get, well, 100%. But maybe if you choose, let's say, 50%, then you can measure how much of this area is relative to the total area. And maybe it's not so interesting for this circular object, but you can imagine if you have some sort of kind of seed that is skewed. So maybe it's going to be like very, let's say, fat at the bottom and then pointy at the other end. You can get a number to detect this kind of skewness. We also have a feature called beta shape parameters, where without getting too much into the mathematics, you can kind of imagine that you try to fit this shape as well as possible. And without knowing the technical details, you can imagine that, so this border this function fits the shape as well as possible. And what you get out are these numbers. So A and B are parameters that define this shape you found, and shape match is a number between 0 and 1, which tells you how well this shape actually matches your, or the fitted function matches the shape. In this case, you would get a number close to 1 because it's a good fit, but you see it's not a perfect fit. And then you can get some other measures too. You can get the skewness and kurtosis as well. So from statistics, it's the 3rd and 4th order moments. Okay. Then we have blob side regularity, where Imagine that you put in 4 lines for this shape, and you want to measure the deviation from a straight line. So we put in the bounding box, and then you measure if there's any kind of deviation. So here, in this case, you use this feature for detecting if some kind of object is broken in some way, as you see here. Then, as previously mentioned, you can use compactness and compactness ellipse, where you measure the deviation from a circular shape. So I put the formula here if you want to see them as well. But you can kind of imagine that the compactness is just a measure where you try to measure how close it is to a circle. So if it's 1, it's a perfect circle. And the more away you get from 1 down to 0, the more away you get from a circular shape. And for those interested, this is the way you measure it. So in the numerator, you have 4 times the area. In the denominator, you have pi times the length squared. And you can do this as well for ellipsoids. But instead in the numerator, the denominator, you see instead of having the length squared, you'll have the length times the width. And again, if this one is close to 1, then you have a very elliptical object. The more closer you get to 0, the more away you get from this elliptical shape. And again, you can interrupt me if you have any questions. Some more measures for circularity. You also have eccentricity. This this measure is a measure of the ratio of the length to the width. So you can imagine these numbers if they are the same. So if the length is the same as the width, so in a circle, you'll get a 0 here. And the more different they are, the more closer it will be to 1. Let's see, form factor and roundness. Without getting too deep into the math, they measure roughly the same as the compactness. So these two are also measures of how circular an object is. Then we also have the horizontal length features. So I think maybe you should only focus on the length mean and mean profile, but the length mean returns the mean of the width of horizontal slices in the blob. And what do we mean by that? So you define a number of slices. So let's say you have this shape and you define 20 slices given by these arrows here, these cross sections. And then you will measure the mean width within each slice. And those are the numbers you then get out. So you get all these slices, you get the mean, and that's the number you get out. You can also get a profile, so where you use this feature, but instead you say, okay, I want 5 bins or 10 bins. So you would subdivide this shape into 5 equal parts, and then use this feature within each part. So instead of getting 1 number out, you get 5 numbers, so 1 for each bin. And exactly the same for vertical length. So instead of the horizontal, you can get the vertical means. And the idea is the same. If you want the mean, you choose how many slices you want. You count up the length of each slice, and you take the mean of that. Or if you want a profile, you define the number of bins again. Let's say 5. Within each bin, you compute the mean of the slices. You can also get measures so that the image-oriented box ratio. So here you measure the area of the entire block, and so the white area here, and the entire area of the oriented bounding box. So essentially, how much does this blob fill the area? You can imagine if you have a rectangle, this number would be very close to 1. If you have another shape where, for example, maybe this is around 80. So this feature measures how much of the bounding box is filled by the blob. You can also get the rectangularity. So here you see, instead of having the image-oriented bounding box, you have the blob-oriented bounding box. And this one is similar. We measure how much of the rectangle is filled by the blob. Then there's the largest hole in blob. So if your blob mask like this has a hole and you want to measure the largest hole, then you can get this by this feature. Then there are some more complicated, more advanced, but also very important features. So the morphology area feature requires that you do read up on, so you can say morphological image processing operations, so dilation, erosion, and so on. But this feature allows you to take one or two operations and put them in a sequence. So for example, you could dilate the image where you increase the size of the mask, or you could erode it where you decrease the size, or perform other operations. For example, what I show here is that in this case, in this rice seed image, we want to detect this protrusion here. And after we generate the blob mask, we perform a white top hat operation. So essentially, we get all of these parts that stick out. So unfortunately, we don't only get this part we're interested in. We also get some noise you can see, and these two top parts. But then after doing some post-processing by area, or by length and mean width, you can get this part. So this one is a bit more involved because you do need to read up on these operations here. But once you understand those, then you can use this feature to get useful facts about your image. Next is the non-convex area feature. So to understand this, we first need to understand what convexity is. And a convex shape, as you see here on the left, is a shape where you can take any 2 points and draw a line between them, and no points fall outside the shape. So you see for this pentagon, you can give me any 2 points, and the points between, or the points of the line between those 2 points will always be within the shape. However, for this star shape here, you could actually find 2 points, you can draw a line between them, and one or more points will actually fall outside. So that's what we call a non-convex shape. And you can imagine that, let's say you have a shape like this, where maybe it's a piece of plastic at a factory line, and maybe some piece fell off. We can actually detect how much fell off by using this method. So you could use this to classify good, bad, or broken, good, something like that. You can also get the perimeter. So again, you measure the entire length of this contour here. And we have a few more shape features left, but one of the other important features or type of features is what we call the phi radius shape features. So if you start here at the bottom, so the radius and phi, so phi is the angle of going around. So if you imagine you start around here at 0 degrees and go all the way around to 360, every time you move around the angle, you measure the radius from the center, and that's what you plot here. So of course, for a circle, if you measure the radius going around, then of course the radius is constant. So you will get a graph like this. However, if let's say you start here for this cherry shape, and you go around from, let's say, 0 to 90 to 180 degrees and around, you will get a non-constant radius profile. Because you see that, okay, in some places, maybe it's close to being constant, but you do see some dips, especially around here at the bottom, but also a significant dip at the beginning and the end because of this stalk. And why can we use this? So the way we can use this is then to, you can compute statistics, so mean, standard deviation, minimum, maximum, so on. For example, the if you compute you can say the difference in max and minimum, you'll get 0 here, but you get something different for this shape. So you can use this feature to find differences in shapes. On the way they are shaped in some unusual way. Some of them might have a very different profile from others. For example, as you see in this case. Okay. You can also measure the pointness of a shape. So here you have two numbers. You have the area of the largest half of the blob and the total area. So the way you find this a half largest is that you take the length, you cut in half, you measure the areas on both sides, and the one with the largest area is the one that's the half largest area. And then you plug those numbers into this equation, and that's the pointiness. You can imagine that if a half largest is, you can say, half of a. So if there's a circle, then this number will evaluate to 0 because there's no pointiness. So it's a way of measuring like how skewed or how pointy is an object. So then there's also the top point feature where you can get the point, so the length of the topmost or bottommost points on a blob. Let's see. There's also the volume method. So if you make some kind of assumption that the width is the same as the height, and you think it's an ellipsoid, then you can estimate the volume of an object. And this has normally been quite useful for seeds. So the assumption that the height is the same as the width for a seed is true in many cases. So that's what allows us to actually measure the volume or estimate the volume of an object. And the last shape feature I want to talk about is the width of the blob end. So you can get the width at either the widest or the narrowest end of a blob. Okay, so moving on to texture features. So in this case, we don't have as many but they are equally important. So you could measure the autocorrelation, where essentially, let's say you take the image and you shift it by some amount, let's say some steps to the right. And then you have you measure the correlation between those two images now. So, and we'll have an exercise on that today. For example, if there's some kind of structure that repeats itself, let's say you have some spots, you have a seed with spots, and the spots repeat themselves every 3 millimeters, something like that. You can use this feature to then calculate this repetition, this repetitive structure. Then there's something called basic image features, and so this is where you measure 7 what we call basic image features, and you get those numbers out, and we'll get back to that, what that means. You can also measure the directional texture, so that's actually what we show here. So you see this blob has some kind of streaks in the vertical direction, and we want to measure those streaks. So if we look in one direction, so at the top, you can see we can identify these streaks. And this could be important because some blobs might not have these features, but others will, like this one. You can also measure holes in there. So this one is more elaborate. So if you have insect images, you would measure the holes like that. And the others, let's get back to those. So autocorrelation, again, you take the original image and you shift it. So you generate a new image by shifting the original image. And then you can use those two images to find the correlation between the two and get statistics from that. And again, that's used to find out if you have some repetitive structure. So again, if you have a seed with spots and they repeat themselves every 3 millimeters, either going up or to the right or left, then you can measure that. Also, so basic image features is a bit more involved because it does require that you read this paper. So on the left here, I took an extract from the paper itself. But if you want to know a higher level understanding of it, you can look on the right. So basically, it's where you choose 7 filters, you run them across the image, and then you calculate statistics on each of these images. And they measure different responses. So you can use this feature out of the box and just get a vector of 0 numbers to measure different parts or different things in an image. Okay, so the directional texture is a measure of the directional texture in a blob, and is defined as the ratio of vertical orientation energy to horizontal energy. So what you get out is you get the ratio of these two. You also get a number for how much the directional energy there is in the horizontal and how much there is in the vertical. So without delving too much into the algorithm, if you have an image like this where you see there's a clear direction, let's say in the vertical, then you would expect this number to be quite high. But if you have another blob where maybe the direction is horizontal, then you will get a high number for this energy. Let's see. This one might not be, I think this one is more relevant. So MSI hole detect. So before I talked about largest hole in blob, but that was when the blob mask had a hole in it. Here in this case, there's no hole in the blob mask, but there is a hole in the insect or in the maize kernel, which you want to detect. So how you use this transformation or this feature is that you define a transformation, as you can see here in the second image, where we clearly see where the hole is. In the fourth image, you have the mask you get from it. You do some post-processing, and that's where you actually measure the hole. So again, you can use this for applications where, let's say you have maize with insect damage and maize without insect damages. And then you can use that to classify those two. The last one, so the orientation histogram statistics gives a histogram of the oriented gradients. So it's based on edge detection. So first you compute the edges, and then you compute the magnitude and the gradient information. And then you get 7 measures out that give you information on this. So again, if you have some sort of direction in an image, I would advise using this feature. Moving on to contour features. So we have around 10 slides left. So for contour features, there's again not so many features, but they also do very specific things. So contour features, they characterize the contour. So in contrast to the shape features, the contour features, they operate on the blob contour. So, and what's the difference? The difference is that, so we have the mask here, which is what the shape features operate on, but the contour is the border of the mask, and that's what the contours operate on. For example, you can get some statistics on the curvature. So how much you can say the contour changes. For example, you see there's a huge change here when we go down here. Suddenly we have a very sharp edge and a valley. You can also measure the number or the largest straight runs, and I'll get back to what that means. You can also measure if there's bumps or there's these indentations here. So Again, first, what is contour and how do we actually calculate it? So if you start here on the left, so at each point on the contour, you look in the two directions. So you measure the angle between this point and a point some distance away in one direction and another direction. And then you find the angle between those 2 points. And as you can read here, if you have 180 degrees, if it's less than 180 degrees, it's an inward bend. If it's more than 180 degrees, you have a bump. So essentially what you have here, since this is below 180 degrees, this is an indentation. And this one, I think, is maybe a bit bigger than 180. So this would be a slight bump. But you can imagine if there's some kind of thing that sticks out, it will have a large curvature much greater than 180 degrees. And what do we measure here on the right? So this is just the curvature for every single point. So you can imagine for every point you go around 360 degrees, you measure the curvature, as we see here, in every single point, and that's what you get in this graph. Okay, and then using that, you can then detect the number of bumps, the relative bump length, the number of indentations, and so on. And you can also get statistics. So you can, using this graph, you can get the mean, the median, the minimum, and so on. And contour straight runs simply returns the length of the longest part of, so you can imagine you have a blob, and maybe one side is very straight and the others are round. You can actually measure the length of this part, which is a straight line. So it simply finds the place on this contour, which is the longest part, which is a straight line. Okay, so the last few slides are about machine learning model performance. So how do we actually quantify how good or bad a model is? And we need this information in order to compare models with each other, but also to find out how we can improve our models. So I'll talk about what are confusion matrices, what is cross-validation, and what is a test set. So first I'll give a high-level overview, and then we'll go into details with each of these. So a confusion matrix is a visualization of the performance of a model, and it's a 2D table of the actual and predicted classes. And the reason why it's called a confusion matrix is because it makes it easy to see if the model is confusing the classes. So, and the way we then measure performance or estimate performance is that we use five-fold cross-validation. And I'll get back into what this means. But it's a method for estimating the performance when you do not have a test set. So the idea is that you take a data set, you subdivide it into 5 equal parts, and you take one of the parts, leave it out, and train on the rest. And you do this 5 times until you've gone through every single part. However, the best thing to do always is to have a test set, because so I mean, you could go ahead and you could predict how well your model performed on the training data, but that's very biased, and the model will try to fit the data as well as possible, and this will tell you nothing about how the model will perform on other data. And what we strive to do is we try to make a model that generalizes well to new data. So cross-validation is one method where you can estimate this performance, but the best thing you can do is actually to have a test set where once you are finished with training the model, you take the test set and then you predict on that set to get an unbiased estimate of how well it performs in the wild. So what is a confusion matrix? And on the left, you see the diagram. On the right, you see a summary of the information I'll tell you. So on the left, you see that we have the actual classes and the predicted classes. So this first row here you have all the blobs or data points that are actually class A. And the first column, first row, are those of class A that were correctly predicted as A. And the second row, first column, are those that are actually A but falsely predicted as B. Same for the second row. You have those that are falsely seen as A and those truly seen as B. So that leads to the concept of sensitivity and specificity, or true positive rate and true negative rate. So imagine now that you have two classes, let's say positive and negative. So of all those that are positive, the ones that are seen as positive, those are the true positive. The positives seen as false negative, predicted as negatives, those are the false negatives. And the same with all of those being negative. Some of them are seen as positive falsely, and the ones that are truly negative predicted as negative. So here we give a practical example of how this could look. So let's now imagine that the damage. So you have a case where you are training a machine learning model to predict whether a seed is healthy or damaged. And the model has been trained on 300 healthy and 300 damaged seeds. So here you see that of all the damages, it finds 50%. And of all the healthy seeds, you see the performance is quite adequate. So it finds almost all the healthy seeds. So what can we see from this table is that it has a bad performance on damaged seeds, so it has a low sensitivity, but it has good performance on healthy seeds, so high specificity. So what this table tells us is that when you show the machine a damaged seed, it's kind of up for grabs. It's 50-50 whether it's going to be healthy or damaged. So we cannot trust the model beyond this. However, if you present it with a healthy seed, we can be quite certain that if the model says healthy, then it's actually healthy. So now this table tells us that we need to do much more work on actually finding the difference between healthy and damaged seeds. And the final slide here is now on fivefold cross-validation. So imagine you don't have a test set and you still want to measure or estimate the performance of your model. Again, on the left, you see we sketched out how the process works, and on the right, we summarize how it works. So you have your data set here in green. You subdivide it into 5 equal parts. And then over 5 iterations, you choose an odd one out. So you leave the blue part out, you train on the rest. And once you train the model, you test on this odd one out. You do this 5 times. You record the predictions in a confusion matrix, and then you get an estimate of your performance. So again, this is the case where you do not have a test set. So it's always better to have a test set where you have the data set you train on, and then after training, you take out this test set and then get the true performance of the model. And those are the slides. Any questions before we move to exercises? Also here. Yeah, Sweta, you have a question?
We can go to the slide number 40 or 41. The previous one. Yep.
Yeah.
See, in most of the cases, this is for the damaged and healthy. So now we know, like in this lower case, the 5 seeds which has gone to the damaged seed, but we know that they are healthy. So how can we change or train the model to get them back to healthy seed?
Okay.
This has happened with a lot of cases in our case. We know that this is not the right. So what would be the thing we can do to remove them, or how we can improve then this accuracy? Like 50%, we cannot present this model to client.
Exactly.
right?
Yeah. Indeed.
Yeah, they will not accept it.
Yeah.
So
Indeed.
we have to increase the accuracy.
Yeah. So the first thing we can do. So you mentioned the 5 mistakes here. So
yeah.
So there's something the table is not telling us, which we could this information we could get from looking at the scatter plot, for example. So maybe these 5 seeds are outliers. It could be that they are so different from the rest that maybe they are broken, maybe they are small, maybe they are different in some way we have not accounted for. If this is the case, then we need to develop features to capture these 5. Or potentially get more data. If they are not outliers, then there could be something in the features which needs to update. So that would be the case for these 5 here in the healthy department. For the damaged seeds, this case seems to be more clear cut. In this case, I would say the features are not doing what they're supposed to do. So we need to go back and look at the features and see. Maybe we forgot to put some features in. Maybe the transformations are not working. Maybe we need to change some parameters. So in this case, it's purely the features that are to blame, and we need to update them.
Okay.
I hope I answered.
Yeah, you have answered. But you know what happened in case of Advanta? We were working on a physical purity of the finished product, corn seeds. And, you know, the corn has round seeds and rectangular and all different kinds of seeds. And we were supposed to identify the broken seeds on it and classify them. The variation between a human and a videometer was a 1%. We were showing a higher result than what humans counted. So they said that no, the results are not matching, and we don't want to go ahead with for this application.
Because the machine was better than humans, or?
No, actually it was online discussion was going on. We couldn't take the physically machine at Hyderabad. So maybe in the next trial we will do that so in future. But this was the case. There was a variation between a human versus videometer. The countings and the major things was coming from the round seeds of corn. They lie flat on videometer, and we are not able to see the bottom part.
Yeah.
And if they are broken when they are lying flat, so we can't see what is the difference coming up.
That is a restriction. But if
there is a restriction about it.
What we usually say is that if we assume that 50% are lying up and 50% are down, we can multiply the number of damages by 2, and we'll get a better estimate. Assuming that it's true that 50% are up and 50% are down.
But we have to assume that way. But it's not always the case.
Okay.
It's not always the case. Sometimes in a sample, more round seeds are there. Sometimes they are regular shape. We can't control like how many round seeds are there in a sample and what would be the damage part to that. So we need to give the solution to them yet about this.
Maybe we should talk more specifically about this on when we meet with Carsten as well. Maybe tomorrow.
Okay, maybe tomorrow. Yes.
Yeah.
Sure, definitely.
Do we have more questions?
No, this was the one major one. And the one you mentioned about the contour. Can we use this one to identify the this one slide number 34. This angle in rice variety, the indentation. So we'll try to use this today and see if it is giving us some better result. Okay, and then we'll discuss this also tomorrow.
Okay, that sounds good.
Right, and if we won't understand how to apply this, we will learn it tomorrow.
Okay, that sounds good.
Okay. Yep.
All right, thank you.
Yeah. Bhuvi, make a note of this. Yep.
Yeah, I made a, okay.
Yep. Thank you.
Thank you. Okay. So if there's no more questions, then we'll go to exercises. Let's see, yeah. So like this. So we have 7 exercises for today. So the first one is about the non-convex area feature. So again, remember the difference between a convex and non-convex object. So in these broken maze, sometimes a significant part has been chipped off or fallen off. But if we can actually measure how much has fallen off and use that to differentiate between whole maze and broken maze. So that's the first exercise. We can also distinguish between dorsal and ventral sides of wheat seeds. So that's what we do in exercise 2 with the directional texture. Again, here there is some kind of direction, this streak, not present on the dorsal side. Then we'll separate these OSR seeds here on the right from this gallium aparin seed. So here you see there's some repetitive structure. You see these small dots, which are not present on OSR. Oh, okay, and here you also see that the this contour is quite round, like there's not a lot of curvature, but here you see there's some kind of erratic structure you can measure. And this one is for the length profile. Let's see. Here you to measure bumps and indentations. So here is actually a quite nice slide with. So here there's clear examples on what bumps are and cuts or indentations. And finally, we have here's where you use autocorrelation. So here where you have kind of repetitive structure, you can measure that. And the last exercise is on the orientation histogram statistics. Okay, so I'll stop sharing.
Share our screen.
Yes, please.
Okay.
Okay, I see the screen.
Sorry.
I see your screen.
Yeah. So as you can see, we have applied beta shape parameters.
But the further to the scatter plot that is shown in the step 9, we are not able to achieve it. And plus this in step 7, the value 1, 1.5 greater than 2. I'm confused over there.
See below. So if you click on the feature and click on output options and click on the arrow down and then click on beta shape B, like the checkbox. Yeah, and then go away from that.
Sorry?
Then click left click. No, left click.
Left click.
Okay.
Sorry, your voice is very low. I'm not able
It's
to
very
get
low.
it.
Ah,
Yeah.
okay, okay. Click on output options. On beta shape A, on output options.
Yeah.
And the arrow down. And click on beta shape B. And click on the output options again. Okay, so now we completed step 8.
Okay.
So
So I
if you
can remove this one, right?
yes. And if you calculate, right click and calculate features on blobs and node. Oh, you also do need to click unknown. To
Okay.
yeah, and then right click and calculate. Was that the issue or?
Oh, yeah.
Okay,
Okay.
nice. I also see we have we reached the time limit. Do you have any quick questions before we end the session? You can always write to me, or we can take other questions tomorrow when we meet, or next session.
Sure. Since we are still continuing, we might ask in the next session.
Okay, that sounds good. How about you, Damien? Great, that sounds good. All right. If there's no more questions, then we'll close for today. Thank you, Damien. Yeah, bye-bye. Bye-bye, everyone.